Welcome to week 4 of machine learning for engineering and science applications. For the first 3 weeks we were looking at some mathematical and computational preliminaries. This week we will actually start our excursion into machine learning. So, before we do that, I will be introducing you to the basic learning paradigm that will be used especially for the deep learning module. You might recall that we had split the course into essentially 4 large sections. The first 3 weeks were the mathematical preliminaries. The next set, which will be continuing until approximately week 8, would be deep learning, which is the most popular machine learning algorithm or the machine learning family in use right now. Of course, we never know which algorithm is going to make a strong comeback. So, we are going to concentrate on other machine learning approaches after we finish deep learning, and finally we will look at some advanced algorithms in the last couple of weeks. Now, the paradigm that I am describing right now in this video is particularly applicable to the deep learning set. So, you will see that the various models that we will look at or the various algorithms we will look at will have a sort of standard template. So, what I am describing right now is the general template, so that you see the pattern when we repeat it. Often it is easy to lose yourself into the algorithm without seeing the bigger picture. So, what I am describing right now before we get into deep learning is the overall paradigm or overall template that we will be using here. Before we go to the deep learning or the learning paradigm, I would like to talk about some minor changes in the syllabus as announced in the course at the beginning of the course. So, we have some minor changes. Previously we had planned to introduce applications at the end of each week. So, we finish a week of lecture and then talk about some applications of this as we step into deep learning. However, this had several implementation problems, especially due to the time that it takes usually to complete the week's lectures. That itself is around 2.5 to 3 hours, and if we start discussing applications it would have taken much longer. So, what we have done now is we have removed some really advanced portions which we had kept as week 11 of this course, which is structured probabilistic models on Monte Carlo methods. Anyway, you can do this as part of other courses, and instead we will now devote one full week. This will be around week 8 or 9 or week 9 or 10 of this course, and we will have one whole week after we finish the deep learning portions. We will discuss all the possible engineering applications that have especially come up over the last few years. There have been some old applications, but especially new applications we will be discussing. You will find some surprising instances of this in week 9 and 10, and we hope that you will enjoy that. We will have a concentrated discussion of applications. The other week lectures will of course cover the primary theory and the primary computational ideas that you need in order to implement deep learning, and we will take some standard examples and some engineering examples, but the heavy load of applications will be relegated to week 9 or 10 of this course. So, in this video we will be discussing the following ideas. Most of deep learning uses one simple learning paradigm or one simple template by which it learns. We will now look at some how it is applied to linear regression, logistic regression. I will give you a brief idea and then we will get into the details of this. So, recall we had looked at this in week 1 itself. The standard machine learning paradigm is different from what happens in classical programming. In classical programming you give some data and you give the rules for manipulating data, and that gives you the final answer that you require. On the other hand, in machine learning we actually give the data, the input data, we give you the final answers that are required, and you are supposed to figure out what the rules are. This kind of rules is what I call model. Model means basically how is the input related to the output. So, if I speak and you are hearing words, even though all I am doing is making sound waves in air, how is it that you are translating the sound waves into some words? That is a model. So, that is a model, that is in data terms, it is basically you take a set of numbers and turn it into another set of numbers through a map. So, now let us look at this in some more detail. So, let us look at now specifically the machine learning paradigm. So, what you have is, what comes in is an input data, you also give the output data. Okay. And what we figure out are what are called parameters or weights. Please notice this word, this will be recurring for a long time till we go till week 9, or classical deep learning is all about learning the parameters or the weights. Okay. So, our task is to learn the relationship between these two. This is what we do not know. Okay. So, if we see a bunch of pixels and we identify this as a human being, what is it that is happening there? That is what we want to learn. In classic engineering or science terms, we want to know the model. Okay. We want to know the model for, why is it, what is the relation between today's temperature and yesterday's temperature. So, you can treat today's temperature as y, yesterday's temperature as x, and you want to know what is the relationship between these two. Okay. So, that would be a model. So, we are using the same term as a big umbrella term as a model which relates one thing to the other thing. Okay. So, for now we will think of this relationship as if it is a function. This is the standard model we will be using till we come to the end of deep learning. Okay. We call this function, what is this function? This function that relates x to y, we will call this as the model or the hypothesis function. Okay. Remember, in science we postulate or we have a hypothesis, okay, this is probably what is happening. So, if you have a hypothesis something like the relationship between the two forces of earth and sun is gmm by r square. Okay. So, that is a hypothesis. So, it is a mathematical hypothesis and it is a function. Now, a subtle part is that every function has two parts. Okay. So, let us take one function. Okay. So, let us say x is a vector and it has two components x1 and x2. Okay. And I have my function y is h of x and is given as w0 plus w1 x1 plus w2 x2 plus w3 x1 x2. Okay. Now, this function itself, this function here has two parts. One is the form of the function and another is the parameters of the function. What is meant by form? Form is the fact that the first term is a constant, the second term is linear, third term is linear, and the fourth term is non-linear x1 x2. This is called the form. The parameters are these w0, w1, w2, w3. Okay. So, when you have some x and some y, you can have infinite number of forms, you can have linear, you can have quadratic, you can have cubic, exponential, whatever it is. Okay. And you also have in each one of these, you have some unknowns. These are called the weights or the parameters or sort of the knobs that you turn for this function to look different each time. Okay, if you have a linear function w0 plus w1 x, you have two weights. If you have this sort of a function, you have 4 weights. So, when we say that machine learning learns and what it gives out is actually only the parameters or the weights. So, within the deep learning module, this is the only thing we will be doing. We as users already give the form. Okay, so, suppose I say this is the form of the function, machine learning is not smart enough to say okay, let me also try x1 x2 square. It cannot try any such thing, it can only try within the limit that you have given it. Okay, so, user defines the form, user or the programmer or the machine learning engineer gives this form and the parameters are found by the algorithm. Okay. So, when we look at the learning algorithm, all it learns are just the parameters. Okay. Now, how do you decide on the form? That usually requires domain knowledge. Okay. That is, you need to know how it, we will see some examples shortly, but you need to know what it looks like. So, if you have the relationship between let us say the voltage and the current, you kind of know from intuition or from your physics knowledge that it is supposed to be linear. Okay, somebody working in solid mechanics, stress and strain, they know it will kind of be linear or maybe a small variation on that. Okay. So, the form is usually decided by what you already know from science or from engineering about the function, and the parameters or the weights are given by the machine. In some sense, though this is not quite fair, as you will see, in some sense sophisticated curve fitting is what is going on in much of machine learning. Now, this modeling process which is going to figure out this parameters or weights involves two separate processes, one is called feed forward and one is called feedback. Let us see what these are. Okay. So, let us look at feed forward or forward modeling. So, let us say you have a process of this sort, you give x, you also have to give the weights, and what comes out is y is f of x colon semicolon w. So, a model or a hypothesis, as we discussed in the previous slide, is simply an educated guess at what the relationship between the input and the output is. In some cases it is kind of obvious, in some cases it has not. Okay. So, you usually have two pieces, as I mentioned just now. You have the form, which is linear, quadratic, exponential, etc., and then you have the parameters, the unknown constants, adjustable constants that are sitting there. So, we sometimes use the notation y is f x semicolon. What it means is this is a parameter. Whatever comes after the semicolon in this notation basically means it is a parameter. Okay. Now, notice that whenever I give you x, suppose this is given, suppose I give you some choice of w, okay, I am even guessing w, okay, you can find a y if you are given f. If you are given the form of the function x and w, y is fully determined. Okay. This process of going from x w and coming out with y, okay, is called the forward model. Okay. We will see the significance of this as we go on in the course. Okay. This process is also sometimes called feed forward. Please remember the terms. Feed forward is nothing but putting x and w inside this box and then getting out y. Okay. So, that is simple forward model. Now, however, as I said earlier, what you are interested in knowing is w. Okay. So, this is the way it works. So, let us say you collect lots and lots of data. Okay. So, you collect x, a corresponding y. Suppose we are doing a voltage and current thing. So, you do one experiment current with a particular resistor, find out voltage current, do a second experiment voltage current V1, I1, V2, I2, so on and so forth, you collect lots of data. So, we will call the input as usual x and output as y. Now, I am also going to use the term ground truth. Okay. What does ground truth mean? This is what came out of experiment. Okay. Suppose a standard machine learning example is, suppose you are trying to find out house prices in a particular area. Okay. So, you are guessing that house prices in that particular area cost, let us say 1500 rupees per square foot, but you will actually have to go to the house and see, measure the area, measure the house price, and the price might actually be different from what you guessed. Okay. So, the owner might say, no, I am going to charge you 2000 rupees per square foot. Okay. Ground truth is what actually exists out there in reality. Similarly, if a person is doing a radiologist or somebody is trying to identify cancerous tumor, you go to the radiologist, show him images, the person will look at the scan and say, okay, this person has cancer, that is the ground truth. Now, you have your model which is separate from the ground truth. What is the model going to do? It is going to do a mathematical process. We are going to use a hypothesis function, H stands for hypothesis, that is, you do not know how the radiologist came up with cancer or no cancer, you are going to guess a function. Okay. So, we give a function and for that the user has to give a form. Okay. For example, we say that h of x w is w0 plus w1 x1 plus w2 x2, this is a guessed model. Okay. Now, we do an iterative method just like we did with gradient descent. Okay. So, what do? We initially guess for some arbitrary value of w. Now, once I know x w and I also know the form of the function, this is, remember, already user fixed, this will not change during our learning. Okay. In the middle of the learning, we do not suddenly say, okay, from linear let me switch to quadratic. Okay. Once you have a learning, that optimal learning will happen for a particular form of the function. Okay. Now, what will happen is you will get some h x w, we will call it y hat, in order to distinguish it from y. Okay. What is that? Suppose the radiologist said cancer and you said no cancer, okay, based on your hypothesis function or based on the parameters that you have chosen, this is y hat. Okay. So, this is experimental truth, this is our guess. Okay. So, what happened was x was fixed, w was guessed, y is fixed because that is the truth, and y hat depends on h. Okay. So, our guess gives us some y hat, the ground truth is something else. So, you are going to find out that there is usually a difference between the ground truth, as we will see in several examples shortly in this week. There will be some difference between the ground truth and our hypothesis. Okay. So, what we do is cleverly we say we define a cost function. Okay. So, what the cost function does is that it tells you, well, ground truth was 1 and you said 0.8. So, it is going to cost you, okay, to have this difference between 1 and 0.8. Okay. So, you can have various different cost functions. So, once y and y hat are given, you can actually find out j, which will be the difference between, in some sense, a difference between y and y hat. In general, what is supposed to happen is, if y is equal to y hat, j should be 0. Okay. And there are several functions which satisfy this, which we will see again as the course proceeds. Okay. So, dependent on the difference between y and y hat, we define a j. Now, what we do is we find out that w which minimizes the cost. Okay. So, this is the general idea, this is a very important idea. So, the learning idea of finding out w's is now reduced to a optimization problem, and this is why we did all this optimization in week 3. Okay. Okay. So, we use some procedure such as gradient descent. For example, suppose you know j, then you can keep on iterating and find out what is the optimal w which minimizes j. Okay. So, this idea we will use again and again. So, just to summarize, h is user defined, x and y are data, you guess a w, run it through h, it gives you a y hat. Okay. Now, you find out y and y hat are different, it gives you a cost. Okay. Then once again using gradient descent or some such method, you improve your w. Okay. This process of going from j to an improved w is called feedback. Okay. This is very similar to gradient descent. I have written gradient descent there because as far as this course is concerned, we will only be looking at gradient descent and its variants. Okay. Some variants we will consider the next week, but we will look at gradient descent and its variants for this course. Now, all this process tells you is that what all do you have to provide as an engineer. Okay. So, first of all you have to decide what is an appropriate x and what is an appropriate y for this problem. Okay. So, that is an important part, as I had said much earlier in week 1 itself. Okay. Please remember, all problems, any problem, even a seemingly qualitative problem, can be kind of reduced to a data problem, and all solutions as far as we are concerned will be shown as functions or maps. Okay. You have to choose an appropriate and usually a large data set. Okay. A lot of this is interaction. Sometimes you might choose some nice x and y for the problem, some nice input and output vector, but you might not have it available. Okay. So, you might have to do something a little bit more clever in order to find out. So, you have to find out x and y so that you need a large data set. Okay. So, finding out a good data set is a very important part of the process. Now, you need to decide on some appropriate form of the forward model. Okay. One example is the linear model which I have shown, and which is the first case we will be considering. So, if x was a vector x1, x2, xn, then y hat could be this, which is a simple linear model. The fourth thing you have to decide is what is the form of the loss function. Okay. One simple loss function called the least squares loss function is simply y minus y hat squared. Okay. So, this is a simple cost. Okay. And finally, you have to decide how you are going to do the optimization. Okay. So, like I said, we will be sticking to gradient descent and its variants. An important thing to note is that you will have to give the hyperparameters alpha, etc., is that machine learning is not magic. Okay, so, there is no magic going on here, it requires a lot of input. For example, as we had discussed earlier, this might require domain knowledge. Neural nets try to take this away, but really even there it is as we will see later on in the applications thing, it is usually very useful if you have some amount of domain knowledge. Okay. So, let us look ahead at what we will be doing in deep learning. So, we will be looking at specifically various different types of hypothesis functions. Okay. Now that you know that all that is required in order to learn W is to have a hypothesis and to learn it, we will now be looking at various types of hypothesis. Okay. So, each of these have their own purpose. Okay. So, the type of hypothesis that we will be looking at have their own purpose and there is a specific domain where they will be worked. This is like any other model. So, you can think of what we will be discussing as various tools in your toolbox. Okay. So, just like you would not use a screw where something else is required, where a screwdriver is required. Okay. So, you can have a hammer, you can have a screwdriver, you can have a nut, you can have a bolt, all these could be sitting in your toolbox, sometimes a spanner. Okay. Now, each one of these are different and it is your intuition and your knowledge of the domain that lets you use an appropriate thing at an appropriate place. So, what we will be doing very often is tell you, okay, the use of a spanner is this is what it will do, and you have to find out where it applies. Similarly, we will be discussing various models, each of these models is a different model. Okay. So, linear regression, so usually it is used for simple fits, curve fits. Logistic regression is used for classification problems. Deep neural networks are used for almost any general nonlinear problem, but sometimes it might be overkill. Okay. So, the reason why deep neural networks work and probably why many people are in this particular course is that we know that any function can actually be approximated by a deep neural network or even by a reasonably shallow neural network. Okay. It will approximate any function at all. So, we will look at this next week. Okay. Then there are something called CNNs which will be week 6 and 7 of this course, which is for vision based problems. Then you have recurrent neural networks for time series sequential problems. Okay. So, all these are, like I said, different tools in your toolbox. We will be going through sequentially what the properties are of these. There are also appropriate loss functions for each and every case. It is also possible, this important warning for you, that none of these might be the best model for your problem. Okay. And it is possible that you might have some good idea of what the model looks like, and still the overall paradigm that I am describing in this video actually works for you. So, as long as you have some idea about the problem, use as much knowledge as you have. We will come to some concluding remarks towards the end of the deep learning section on where to use it and where not to use it, but please do remember, use as much knowledge as you have about the fundamental problem that you are trying to solve. Usually that is a good idea. So, while we are going to look at each of these models, we will be specifically discussing the following aspects. Okay. So, what is the mathematical expression for h of xw? This is the first thing that we will be discussing. So, linear regression, for example, is simply if you have w and x, a linear model wx plus b. Logistic regression is, this function is called sigmoid. We will be looking at details of this later this week. This is a non-linear function. You will see that it looks similar to linear regression, and this is the usual process we will follow, a linearity followed by a non-linearity, that is logistic regression. Next thing we will be looking at is what is a good loss function. Remember, your y and y hat will usually be different, and you want to find out, how do I tell the machine that I have not got the answer that I wanted, and that is usually through the loss function. So, the loss function if it is non-zero tells you that there is a difference between your hypothesis and ground truth. So, a least squares function is y minus y hat square. This looks a little bit more complicated, but it is actually a fairly simple function. We will be looking at this. This is called binary cross entropy. Okay. Then we will be looking at what are efficient ways of calculating the gradient, since you are going to get a gradient when we do gradient descent, when we do optimal parameter search. So, for neural networks the algorithm which we use is called the back propagation algorithm. So, in the next video we will be starting our discussion with the first model for this course, which is linear regression, the linear model. Thank you.